When a quantum system interacts with its environment, its internal phase relations scatter. The environment suppresses local interference, a process known as decoherence, which sets the stage for our classical experience. Within the theoretical framework of the quantum to classical transition, we can categorize our progress as a stack. Decoherence and its extension, quantum Darwinism, successfully secure the top three layers. They explain how correlations form, which states remain stable, and how records multiply. But the bottom two layers, the physical origin of probabilities and the occurrence of a single outcome, remain hollow. There is a common view in physics that once the math shows interference is suppressed, the classical world is essentially derived. But declaring the problem solved masks a void in the architecture of the theory. Describing how information spreads across an environment is a separate task from explaining how one specific result becomes actual. The thesis is that unitary dynamics explains how observers agree on a result, but it lacks the mechanism to select which result occurs. To demonstrate this, we first dismantle the unitary formalism to show that the division between system and environment is an external choice, not a mathematical necessity. Second, we will look at why erasing environmental data through the partial trace cannot physically collapse a superposition. Finally, we will explore the TCGS-SEQUENTION framework, which reinterprets quantum records as restricted views of a deterministic source. Finding the same data in many places is a feature of information broadcasting. It is not the same process as one branch of reality being selected over others. Quantum Darwinism suggests the environment is more than a sink for lost information. It acts as a communication channel, a witness that captures and carries records of the system. As a system interacts with this witness, its properties are imprinted on environmental fragments. Observers can then intercept these fragments, like photons bouncing off an object, to learn about the system indirectly. We calculate this accessible data using the Holovo quantity, which measures how much classical information is present in a specific quantum fragment. This chart shows a redundancy plateau. Notice how the information content rises quickly and then levels off. This indicates that even a tiny fraction of the environment contains nearly all the information needed to identify the system's state. Redundancy plateaus establish operational objectivity, the ability for multiple people to agree on a measurement. But this result depends on how we define the boundaries of the system being measured. Entanglement is not a property of a state vector alone. It only exists relative to a specific tensor product structure, the way we partition the total Hilbert space into subsystems. If we slice the space into a standard system and environment, the math shows high redundancy. The observers and the object are clearly defined. However, there is no unique way to perform this slice. Redefining our observable algebra changes the entanglement structure. When these boundaries shift, the redundancy gauge plummets. The object we were tracking effectively vanishes into a new set of correlations.
The universal state does not provide a single, privileged way to divide the universe into parts. To make quantum Darwinism work, we assume a structure based on locality and interaction scales. We must tell the math what the system is before it can tell us it is being recorded. This means the objectivity described by the theory is a conditional result. It explains how records behave once a partition is chosen, but it does not derive that partition from first principles. Even with a fixed partition, we face the outcome problem. After decoherence occurs, the global state remains a coherent superposition of every possible result. We can see the problem by comparing two different states. On the left is an ignorance ensemble, where one result is actual and we just don't know which. On the right is a globally entangled state, where all branches are present. To see what an observer can detect, we apply a partial trace, which ignores the environmental degrees of freedom. The trace operation results in the exact same diagonal density operator for both scenarios. Locally, they are indistinguishable. This statistical equivalence does not mean the two states are physically the same. One represents a single occurrence, the other represents a persisting global superposition. The partial trace is an accounting tool for ignoring information. It simply does not contain the necessary underlying physics required to actualize one single branch and violently delete all the others from existence. Tracing over an entangled environment yields an improper mixture. Unitary dynamics identifies the branches, but it provides no mechanism to select just one to be the real one. If unitary dynamics is incomplete,
we need a framework defining how a singular record is constituted. TCGS-SEQUENTION approaches this by shifting the ontology. The framework posits that the source of reality is deterministic. Probability is not a fundamental lottery. It is a result of how we access that source. In this model, the source is a high-dimensional manifold, casting a shadow onto a lower-dimensional corridor. Because many source points map to the same shadow point, an observer sees possibilities. Quantum probability measures this inaccessible information. Within this architecture, redundant records of quantum Darwinism are seen as shadow stabilizations. They describe how observations become durable for observers within specific corridors. The transition from a set of possibilities to a single record is governed by the extrinsic constitutive law, or ECL. The ECL is a readability law, mapping fixed source content to a determinate shadow record. Unlike collapse models with random jumps, the ECL selects an outcome based on existing content. The global state remains intact, while the corridor's record is singular. This places quantum Darwinism in its proper context. It explains the broadcasting and agreement of information, but it does not create the event. The classical world does not emerge from the suppression of interference alone. It requires a theoretical structure defining the observer's corridor and the law that turns a quantum superposition into a singular, readable record.